All right. Today, let's talk about risk of electric shock, risk of fire. It's actually a super important subject. Most people don't understand it, so there's various rubber stamps you can get, and then I'll have to understand that I see a rubber stamp. Anyone working on anything at any power level, really over like a watt, should really understand the failure modes of electricity. So let's talk about we'll bounce around between AC, DC, talk about what's important, and put words to what actually happens. So I think everybody understands electric shock. It's not that interesting. We run on split phase power here. That means that there's 3 phases bumping around out there. If you read the peak to peak or peak voltage, it's actually quite high. We'll refer to it with the root mean square, RMS. By the time it gets to you, usually, it's 240 volts RMS. That's from L1 to L2, L2 to L3, L1 to L3. You're going to get 2 of those 3 legs, and it's going to have a center tap. And it's literally a trash can full of oil with wires spinning around inside of it with a center tap. Like, there's no magic. Now, if you go to the top of any house or building or the surface entrance, you're going to find 3 wires of the same diameter. Now around here, it's most common to find 2 wires carrying L1 and L2, and the 3rd wire will be aluminum with a single strand of steel. And that's just value engineering to facilitate strain relief. The neutral of mains will never carry more current than L1 or L2. Anyone who says different simply doesn't know what they're talking about. It can be proven very easily with 3 equations, and it can be proven very easily in a layman's test. It's a test of heat. We have current flowing. The heat produced is the current squared times the resistance. I don't know why people can't do. I mean, I do. It's baffling unless you prove it to yourself. You have to prove it to yourself experimentally and prove it to yourself by working the formulas, and you will know it's true. Yeah, I've done a lot of both. So let's talk about that for a second. Wiring mains. So you have a load, it's a kilowatt. You hang it between L1 and neutral. Well, just do the fucking math, right? If it's 250 volts, it's going to be 4 amps, give or take. 4.2 amps, exact. 4.20 amps. Alternating between L1 and neutral. If you remove that load, you put that same load between L2 and neutral, you can get all the same results. Yeah? That's the most you could possibly get on neutral is to you just have like peppers in them. Is to run a maximally imbalanced load. That would be maximizing the load on one side and minimizing the load on the other. You're simply limited by the breaker on the energized side. So people get all weirded out by AC. They're like, well, 6.215144. Okay, so think of it as being 180 degrees out of phase in a 360 degree total phase cycle. Technically, it's 120 degrees. Very few people talk about that. For all practical purposes, and absolutely for layman's purposes, you can consider L1 and L2 out of phase by 180 degrees. Don't listen to any of the analogies about whack-a-mole or water flowing. All of those break down. I've yet to hear an analogy that will give you a feel for it that you need, other than fucking understanding it. I don't have to tell you, dude. The experiment goes like this. Put your 1,000 watt load, which is a heat gun, L1 to neutral. Put your 1,000 watt load, L2 to neutral. Each time you do that, measure your voltage, measure your current with a clamp meter or with a kilowatt meter. I don't care. But we're going to do 240 stuff, so the 125 tool won't work. Use a DMM and a clamp meter. Make sure you don't have to zero out a clamp meter for AC. The clean clamp meter I display will give you an accurate reading, plus or minus 10%, eh? And the fluke I show will work. Now, of course, you're measuring L1 current and confirming fucking Kirchhoff's current law, dude, that if 4 amps is alternating on L1, that 4 amps must also be alternating on neutral. And then when you flip it over, if 4 amps is alternating on L2, that 4 amps must also be alternating on neutral, right? With no current going through the other leg. That's the key, is there's only 3 fucking nodes. There's L1, L2, and neutral. And so there can only be 3 places you need to measure current. And current is the only thing that can create heat through the effect of I squared times R. R is the resistance of your work. Bro, you can't, Tesla douchebag, just passed me on the right and then ran the red light and then swerved across the intersection. It's one of those white Teslas, I'm telling you, they're fucking on autopilot. Now, here's where it will all click for you. Get 2 1 kilowatt loads, as identical as possible. 2 matching heat guns. Just go to fucking Harbor Freight and buy 2 of them. Or get 2 house heaters with the same. Just make sure there's no like funny behavior to them. Yeah? You just want a fucking raw load. It doesn't matter. 1,000 watts, L1 to neutral. 1,000 watts, L2 to neutral. What does the nodal analysis show you? What's the superposition come out to? You're going to converge on 0 amps on neutral, and you're going to see the exact same current on L1 and L2. You have to. Once you get to 0 amps on neutral, you have to have the same current on L1 and L2. It's Kirchhoff's current law, dude. It fucking is fact. You can't break it. It's physics. So how do you prove that? Well, once you attach a 1 kilowatt load from L1 to neutral and from neutral to L2, just cut the neutral line. And then you're guaranteed 0 amps there, right? That's the way the original proofs are done with rocks and sticks, dude. You disconnect the neutral line and you know what will happen? The loads will continue to operate just fucking picture perfect fine, dude. They will run fine. The current will present as normal. The voltage will be equally divided. No current. So remember, you maximize neutral, which is difference current, by doing a lopsided load, and you minimize it by doing a balanced load. Now, don't ask the next question, which is what DC electronics guys always ask. Well, what happens if I put a 100 watt load in series with a 1,000 watt load and then just put that across mains? Don't do that. That's why we produce neutral for you. Right? The current in a loop must be equal. If you have 2 things in series, their current must be equal. That fucking won't work out for you, dude. You're gonna end up with a real bad loading situation. That's why we give you neutral. Neutral lifts sometimes. Think about this. When you're first attaching a plug to the wall, do you think it's instantly and perfectly energized, or do you think maybe one prong makes contact before the second? It's guaranteed. In fact, if I instrumented your plug, any plug, and you attempted to plug into the wall and get them to perfectly coincidentally, or within, you know, a millisecond or 10 milliseconds or whatever, but, you know, if you attempted to attach a plug such that both made contact at the same time, it would be statistically impossible. It is guaranteed that when you plug something in, that for a while, it's either got only L1 or only neutral attached, or only neutral and not L1, you know, one or the other. And then the second one makes contact and the circuit is completed. In that period of time where, say, you have only one leg attached and you don't have neutral attached, this is the case where we're doing a test of taking a 120 volt piece of equipment and plugging it into a NEMA 5-15 outlet. It matters not. And here's why. This is what gets into like fire and like electrocution, shit like that. Because your housing is one of two things. It's either insulated, isolated, or it's ground chassis, earth ground tied. So when you touch something from the outside, you don't get electrocuted when like L1 is attached internally. First, because there's isolation there, and that isolation is guaranteed through a high pot test. Nobody attaches mains intentionally to case. If they do, they've created an electrocutor, and you'll find out right a fucking way, right? So then it happens. Sometimes a wire will flip off and touch chassis, and it used to energize chassis. And I remember as a kid, dude, there was all kinds of shit from the 50s that fucking electrocute you. Well, the way that was solved is that the chassis of metal things gets tied to earth, and back home at the box, neutral is tied to earth. So neutral and earth are at the same potential. There's no current flowing through the ground lines, so they, you know, present a little bit different. They're not loaded by, you know, a return difference current. But if you just turn everything off and take a measurement, they're like 1 ohm off, right? They literally screw together, like with big screws this big, like the white and the green wires screw together. So if you energize the case of something, like say you put L1 hot to case, what you're doing is you're directly shorting L1 hot right back to fucking neutral difference current, and you blow your breaker. That's why you have breakers. One of the 3 reasons you have, let's not get into my whole talk about exactly why you have breakers and exactly why you have bonding. But you have a little tool, you stick it in the hole, it gives you a green light, it says, yep, this socket is wired with the correct polarity. Neutral and hot are not swapped. Hot and ground, you see, neutral and hot, I can't remember the 5 things it reads off, but basically you get a green light and you're good. It detects an open ground, it detects a neutral to hot mismatch, it detects a neutral to ground mismatch, because what it does is it knows that neutral and ground should be the same, so it can, you know, light that circuit. And it knows that hot and ground should not be the same. Right? It's really, if you open it up, it's a fucking simple circuit, dude. Do I have a flat tire? Yeah, so most commonly when a product is sold these days, it has an insulating case. And this material isn't just an insulator, it has a temperature rating, like NEMA rating, meaning that it doesn't make for a very good fuel. If you take different plastics that they'll behave differently. So set to the side how thin or thick a plastic is. Let's say you have 2 identical sheets of plastic, each of them is 1/8 inch thick. And each of them is exactly 4.20 by 4.20 inches. All right, very common, extremely common. Yeah. Now, one is a flame-rated plastic, and one is not a flame-rated plastic. So you mount those in a fixture. Like, remember using a boiling flask in high school or junior high or whatever? You know, just like a contraption to hold it still. Light a fucking Bunsen burner underneath it, and set up the time-lapse video and watch them burn. What you'll find is that there are curves associated with the way something burns. Some plastics will get into a runaway situation where the burning of the plastic starts fueling the fire. Remember, fire needs heat, it needs oxygen, and it needs fuel. Well, this plastic starts really quickly converting into heat and fuel, and it just sucks oxygen, and it burns faster and faster and faster. Now, other plastics are built up in such a way is that that the phase change to release the fuel, it consumes so much energy that it takes quite a big flame to get them to burn. Now, all plastics will burn. You put them in an incinerator, they will fucking burn. You put a blowtorch to them, they will fucking burn. The question is how long can they wait before they get into a reaction which keeps going, right? Remember, what's that called when you start a reaction and then it keeps going? Let's see if I can remember my fucking chemistry. Pause for a second until I remember the key word. For, like, when you're creating mercury fulminate, there's a certain point where it starts self-reacting and the reaction takes off without you. You need not add any more heat. It fucking creates enough heat to keep its own reaction going. Self-sustaining, whatever. The word will come to me as soon as you turn the camera off. So the difference between a NEMA-rated flame retardant or flame resistant plastic and the wrong plastic basically boils down to how good of a fuel it is. And my personal understanding of it that I use in testing is to think of it as a phase change, right? Like, plastic itself, all right, it's not a very great fuel, right? But if you heat plastic up, it will first liquefy. And then after it liquefies, it will gasify. And if you do it, in such a way, you can get it to just carbonize and embrittle, right? It's this liquid or this gas or somewhere, some isotropic, sweet spot of like stoichiometric bliss, where the fucking plastic becomes a fuel, right? So if you formulate your plastic such that it is tough, it is hard. So first you want to raise the boiling temperature of the plastic, or I shouldn't say the boiling temperature. Something's a solid, and at a certain point it will go through a change where it becomes malleable, and then at a certain point farther, it might jump straight to like a gas, but it has to like transition even momentarily through a liquid phase, right? So make it harder to do that. And what they do is they use special plastics with a higher what's the word for that? Fucking can't remember my words today. I didn't prep for this. What is it when something transitions from a solid into malleability? Glass transition. You raise the glass transition temperature. All right. So first of all, you're going to stand off better that way. And mind you, all plastics, they're not meant to hold back a fire for 4 hours. Otherwise, you'd have fucking plastic fireplaces. Okay. They're meant to survive an instantaneous event that is a really high temperature, an ignition event. And this is like, say you take a 20 amp breaker and you take two pieces of 12 gauge copper and you put them in a lathe or in a mill or in some kind of vise that slowly moves them together, right? And just like arc welding, you start going, bah! Arc welding, all right? That creates a lot of heat, a lot of sparks, little balls of molten metal flying around, shit like that. So it turns out that entire event, I've seen it go for like, 10 seconds, only in real perfect conditions. Ultimately, it usually goes for like a second or 3 seconds, and it's an event, right? This is why you have no combustibles in a spot like that. This is why you use like little aluminum cages. This is why you use flame retardant plastics, because surviving something like that is actually quite, standard and normal. It happens all the time. You just don't see it because it happens inside of things. But I'm a guy who takes things apart which have gone through failure. Do you understand how many things I have taken apart that have catastrophically failed? like thousands. I couldn't even begin. You know, you'd have to first start with a sector and then start paring down, and then I could just start listing off jobs for you and exactly what I found on the inside, and you know exactly what's going on. The bigger the power, the more likely you're going to need something like a metal box. But at most stuff, like 1,000 watts, dude, no. Look at half the stuff in your kitchen. Take it apart. Go to your kitchen. Get that screwdriver I like, and get that bit set I like off Amazon. Go to your kitchen and just start taking shit apart. But for this experiment, leave it plugged in while you take it apart, because that's how I usually operate. I take shit apart while it's plugged in. And then you'll figure out where the fucking sparkles are, eh? Wear your safety glasses. So anyways, the TLDR is that, like, the blue boxes used in electrical, you know, AC electrical, and the plastics you commonly find on legitimate products are NEMA rated flame retardant plastics, and they do this by raising their glass transition temperature and by making it creating a situation where it takes a lot of work from the ignition source in order to get the stuff burning. Now, will it burn? Fuck yeah, it'll all burn. If you go back to my original experiment where you attach the two 4.20 inch pieces of 1/8 inch material in a clamp and light fire underneath them, they will fucking burn, dude. But, you know, if you put a blowtorch underneath them, of course. Now, some will burn more aggressively than others. Some will completely self-extinguish. That's very expensive plastic, and then that will have other problems. And you gotta have a trade-off between how brittle it is, how expensive it is, how heavy it is, what color it is, how UV resistant it is, what textures you can get. This is a really, really well understood thing, and I'm sure other people can speak to it much more effectively than I can. So we started out talking about electrocution and fire, right? And I told you a little bit about single phase power, and let's finish that thought off so I can leave it behind. People don't understand how the neutral wire works in their electrical system, and so they have superstitions and misconceptions. So it's very easy to set up a piece of plywood with you know, L1. How about you just go buy a breaker box at Home Depot and throw it down on a piece of plywood and fucking hook up a NEMA 1450 cable to it, because you need some power, right, to you know, execute on a lot of these tasks. You could do it at lower power, but you don't want to be hitting the breakers early and shit. Okay, electrocution. If you take a 1,000 volt battery, so the electricity, people don't understand. The only way you get electrocuted is if you're across the potential. So if you build a 1,000 volt battery and you stack it on styrofoam ice chests in a dry room in Arizona, all right, and you walk up and you touch the positive terminal with your index finger, you're not going to get electrocuted. There's no path to ground. Now you got to be careful. In some cases, that's why I said stack it up on ice chests to actually create like feet of insulation. If you had like a battery sitting on the ground with like nothing but a tarp underneath it, sometimes you can build up like you could build a capacitor. You could build up some parasitic capacitance, and at the moment of contact, dude, a fucking collected charge can bite you hard. So that's happened to me a lot with 120 volt, 120 volt DC, where, you know, usually it doesn't get me, but every once in a while at first contact, it fucking bites me. And that's only when I touch across both leads. 120 volts really isn't enough to do it. But you get up to 1,000 volts, dude, you can start to get all kinds of weird shit, dielectric breakdowns. You get the voltage high enough, it'll jump through the air. You get the voltage high enough, it'll travel over fucking non-conductive surfaces on greases and stuff. You can see it, dude. One of the coolest things you can do is hook up 1,000 volts to a like a large circuit board, and then just start doing stuff like dripping water on it, dude. And you'll actually see the fucking lightning bolt start, then you'll see the little trails where it chased the water off and boiled it off. So nobody really works with 1,000 volts DC. We will be very soon, and a few people are, but for the most part, nobody's working with it. We're talking about like 120 volts AC. It's like 377, you know, like under 420 volts. So there's no magic woo-woo going on, and you know, high pot tests are still, you know, like you're passing a high potential test at like 1/10 of an inch, you know, like that's all it takes to hold it off. Clean 1/10 of an inch. Now if you go ahead and put some fucking rat turds in there, well, you might find out that 1/10 of an inch is insufficient to stand off 240 mains, right? Of course, you know. So when you're rating something for its standoff, well, actually we were talking about being electrocuted, right? People don't care about that. All they want to know is how they're going to get electrocuted. Okay, you're at your house. Are you getting electrocuted by 240 or 120? You're getting electrocuted by 120 in almost all cases. All right? There's three kinds of electric shock you're going to run into commonly in a home. One is what I call a neutral bite. This is where you know just enough to be dangerous, and you're wiring hot. Your wiring box is hot, whatever, you got hot wires around, you got the fucking, you're touching stuff. Dude, we work hot, always. Okay, first, stand down. Understand that anybody who works electricity, after a fucking certain period of time, you're gonna spend a significant amount of your time working hot. It's just, you don't fuck around. It's like, let's say you bang together a box and you got load and neutral swapped, just fucking grab it and swap those back out, dude. You know, unless the breaker panel's right there. Like, if the, you know, if other people are using tools that are plugged into that fucking line, she's gonna leave it on, dude. Fucking wiring hot thousands of times. So what happens? Well, you touch earth and you are earthed. So first understand that even though you're wearing tennis shoes or this or that, anytime you're a human, just consider that you're earthed, okay? You are of the earth. Now, if you touch a green wire, that's earth, you know, nothing gonna happen. If you touch a green wire and something happens, something's very fucking wrong. You are energized, you are not earth. If you touch the white wire, you'll get what's called a nibble. You know, you'll feel it. It's not like catching the fucking main, dude. It's not like throbbing, you know, the 60 hertz dance, dude. I've grabbed handfuls of fucking L1 with wet hands, dude, wet feet, barefoot on fucking, you know, conductive ground. I know what it's like to be fully fucking electrocuted, dude. And I've had many nibbles. So when you're getting nibbled by neutral, that's just literally like the difference current coming back and materializing over the impedance, creating like 20, 30, 40 volts, you know. So it's just like a 40 volt AC nibble. It's not, you know, it's not a big deal. 20 volt AC nibble. That's not, you know, the big surprise. when you're swapping wires or you're working on something that's hot in field conditions, and you know you're holding, you know, something in your hand carefully, and it has the gold screw and the black wire and the silver screw and the white wire and the green wire or the bald wire coming at the bottom, and you hold it like this, and all of a sudden you get bit, right? Well, that's a path between your fingers. It doesn't go through your heart, and you know it doesn't cause you a full body spasm, but you fucking feel it, you know. It's a bite. It's the best kind of bite, dude. It's fucking, because it's just between your fingers and not through your whole body. There's a huge difference in how it makes you feel and how you react to it. In that case, you are actually touching the L1 240 volt line, but relative to the difference current, the neutral, right? The center tap. So there's only 120 volts of potential there. There will never be more, like 130 max. RMS, root mean square. Not peak to peak. You'll be disturbed if you start looking at the peak to peak numbers of what AC can generate, dude. Just think of it as RMS. So in 99.9% of the cases, when you get electrocuted in the house, that's just a simple my fucking wheel's vibrating. It's just a simple 120 nibble, or a bite, or a full-on electrocution. So how would you, it's very hard to get electrocuted by 240 volts. And in fact, you can fucking certainly do it. It's far more likely to get hurt by 240 volts. And this is where you drop a tool across the 240 volts and it instantaneously explodes in your face. So the wires are scary, from the transformer into the house, into your conduit, through your meter, into the conduit, into the box, into your breaker box. Now, once you get to the breaker box, modern breaker boxes have a main breaker, or you might have a main breaker outside. Then, there's still an explosion when you drop a tool on it. It's just not as fucking catastrophic. When you're dealing with raw mains with no breaker whatsoever, and you drop a heavy tool across it, it will keep fucking discharging you to the tune of hundreds of amps, dude. Many, many hundreds of amps at hundreds of volts, right? Well, so what's 100 times 250? All right, 250, that'd be 25 kW, right? 100 kilowatts, so imagine 100 horses kicking in your face, dude. I've fucking done it, dude. It just turns steel wrenches into vapor and they disappear. That vapor occupies a very large space and a lot of it doesn't go smoothly. So a lot of that is liquefied and a lot of it turns into shrapnel. So that's what happens with 240, that kind of fucking injury. But you can get across the 240, especially when you're working on a service, any kind of panel, be that the main service panel or a sub panel, because the two rows are right there. Right? You just reach in and fucking touch them, right? Or you can reach up and touch the two fucking screws. Now, if you have your hand in the box and you put your screwdriver on L1 or L2, that's a center tap electrocution. That's just 120 volts. You'd have to actually get across the full 240, and that's lethal, dude. Like, I'm not gonna say 120 isn't lethal, but I've been shocked by 120 over 1,000 times, all right? You get used to it. 240, the worst fuck up I ever did, I was troubleshooting a hot water heater before I knew what I was doing, and the wires were black and white, not black and black. So I mistakenly, my car's falling apart, assumed that was 120 volts. Because back then, a lot of shit was 120 volts. And I grew up in fucking trailers and shit like that. Sure, there's all kinds of 120 volt equipment. There's this whole ethos of 120 volt equipment for light duty. Well, it was 240. You want to know how I fucked up? I didn't have a meter, and so I grabbed an old 100-watt light bulb. It was a big one. It might have been a 200-watt light bulb. It was one of those weirdo light bulbs you saw back in the day, incandescent. And I tried to touch the wires of the light bulb. Only thing was, it was 240 and not 120. And at first contact, you don't realize it, but every time you connect something, there's a spark. And so when you do it in your hands while you're squatting in a closet in the fucking dark, dude, it seems like a bigger spark. And then you jerk, and then the wires both hit the screw part of the bulb, and then the big fucking sparkles, the explosion happens in your face, dude. I was picking fucking shrapnel out of my face. Other 240 mains incidents, lots of times I've had frayed extension cords, things like that, just, the wires just start touching. And usually that happens like 20, 30 feet away, and it's kind of a non-event. So in a house, you get electrocuted by 120. I mean, so long as you're not like in the breaker panel, right? Like the most you're gonna get electrocuted by is 120. You'll feel it and you go, I'm not gonna do that again. And what protects you from that are housings that are either metal and grounded to earth, along with breakers, and a center tap neutral, or insulated, like your laptop power brick. There's 120 volts or 240 running up into your power bricks, but it's inside of insulated cables, which are special thermoplastics, which are, have all these properties where they don't abrade and they don't embrittle and they don't melt easily. Careful, because not everything's that way. You need to be careful when you're buying counterfeit goods. like junk off of fucking Amazon, dude. You have to test that stuff. Check it. Stickers don't matter. You know, there's a place in China where you can buy all the stickers. So, you know, many a men have bought a warehouse full of bunk goods. Usually it's like someone fucked up in the process, dude, and like the plastic wasn't formulated correctly, and it literally is hazardous. But instead of throwing it away, they sell it for a penny on the dollar, and some other guy buys a reel of stickers, they put the stickers on it, and they put it for sale on Amazon. If you don't know that, you don't know anything. You shut the fuck up on my channel. That shit happens, dude. I test everything I've got. Little IEC cable tester? Yeah. It's a heat gun, dude. It's so fucking easy to do. It's weird. People don't know how to test things. If a cable says it's good for 10 amps, just do the math. 10 times 120 volts, 1200 watts or whatever, right? Go get the heat gun out, dude. Hook it up. If you can't make an IEC adapter by now, you're not getting it. Take an old cable, cut it in half. Now one side you've got an IEC connector. Go to go to Gray Bears, get an old computer. On the back of all of those is an IEC connector. Desolder one from a circuit board. It's really fucking easy to get the pin side, which is the load side of an IEC cable. Just hook it up in a loop. So, electrocution DC. You're not going to get electrocuted below 60 volts. You're not going to get electrocuted above 60 volts either. But we set a safe margin. We said below 60 volts, you will not be harmed. You can put your fingers across it all day long. You can lick your fingers and put them across it. What you can't do is like stab needles into yourself and then go across it. So generally speaking, think of yourself, your internal juices as 1 kilo. And this comes from field data. Like, let's say there's the Army manual, and then there's like what that one dude says who's fought in 3 wars over 35 years and lived to tell about it. This is from one of those guys. Don't get into fucking all this resource said this and that one said that, and 612128414471612. No. Listen. Think of your internal juices as a kilo for all practical purposes. Now that changes with really high voltage, like 4, 5, 6, 7, 800 volts, like we deal with in EVs. Your internal juices turn into a short circuit. Okay, so let's not talk about that for a minute. Let's talk about 60 volts and down. Think of yourself as a kilo. Well, if you go and like slice both of your fingers open and stick them across a 60 volt battery, yeah. Well, what's 60 divided by 1,000? Yeah, that's an order of magnitude more. So, onset, like 100 milliamps will kill you, dude. 100 milliamps to the heart will kill you. You can tolerate a milliamp to the heart. You can tolerate 5 milliamps to the heart. You can tolerate 10 milliamps to the heart. Different people, different strengths. Like a 90-year-old lady who's never gone outside and sits in her chair reading Reader's Digest from the fucking 60s, right? She's going to be electrocuted differently than I am, than a man who's fucking, you know, regularly falls off the roof and gets electrocuted about once a week, right? So it depends on what you're made up of, and a lot of it's how you react to being electrocuted. When you're being electrocuted, you better fucking calm down, I'll tell you that. You better get control. I've almost died so many fucking times. You have to get control and decide. And if it's a big enough electrocution, you don't have that choice. You go fish out, dude. So think about that. But for all practical purposes, think of your internal juices as like a kilo ohm. So if you put 10 volts, like a 9-volt battery, directly to yourself, well, now you're at 10 milliamps of current. And so that's where the difference between having dry hands and having wet hands and having greased hands and being calm or being under stress makes a difference in how you get electrocuted. That's what's funny. That's why like the old timers who've done a lot of fucking work, they can just slap fucking hot wires, dude, with their fucking dry old crusty old hands, right? Like, I literally have worked with electricians who that's their fucking meter, dude. They just tap the fucking mains, dude. And they're like, yeah. Sometimes they'll fucking go like that, dude. I think that's a parlor trick. Usually one finger's out farther, so they're really only tapping one, but it looks like they tap two. Just be aware of that. Don't duplicate that. Those guys have dry, crusty hands, and then the insulation of your hands, dude, is like hundreds of kiloohms. Now, contrast that with some little young tender, dude. Some 9-year-old kid with moist little fingers, right? Much lower resistivity to the skin. You get a much higher current flowing. They're gonna get a bigger shock, dude. A shock is when you are the conductor in an electric circuit. So, at the end of the day, you don't leave anything exposed, which is energized. Anything that is exposed and energized needs to be small enough that you can't stick a finger in there. Some specifications will say that, you know, like you can get special certifications that say, you know, there is no hole larger than 1 by 1 millimeter square, and you have to put like meshes over your fucking openings, and there's all kinds of shit like that where required. Usually that's to keep bugs out. Like in higher voltage circuits, bugs get in there. You'd be surprised, dude. If you've got some fucking box outside, like let's pick on ChargePoint. They've got a box that sits outside and it's warm, right? So it's attractive. It's got lights in it all over it, so it's attractive. It's a fucking, it's a bug light, right? You ever seen a bug light? You ever go to the fucking south and see a bug light? It's just nothing but a fucking bright light that the bugs are attracted to, and then they get their ass electrocuted in a metal cage on the way in. Well, ChargePoint has a charger that goes outside, and it has like blaring LEDs on the front, and it has like a color screen, and it's running, you know, a computer inside, and so it's warmer, and so go figure it, fucking bugs want to go in there. Well, the ChargePoint chargers, you can read, it's publicly listed, will charge it up to 1,000 volts, right? You pull up there in a Porsche, that thing's gonna fucking throw like 950 volts at you. So, bugs are a fucking concern, right? You'll find that if you set up a bug collector and it's not perfectly fucking sealed, which is impossible to do, that you'll fucking start collecting bugs, and then you'll start smoking them off. Like I've opened things up that have like 30 years of bugs, and they just keep piling up, and you know, it's like they get fucking cooked. So most, like, you know, there's lots of places where there's pretty tight cracks between like 480, and what you'll find is one bug will get in there, and the second bug, and then all of a sudden they go ass to mouth, dude, 100% medically accurate, and it fucking smokes them, dude. And then their carcasses are completely dried out, husks, non-conductive, and they lay there, and then the next bug comes along, right? And so you'll see this killing field of bugs. I was picking a ChargePoint because it makes more sense to have your high power back in some really big, like picture a transportainer, right? You want like a transportainer full of power, and then you want nodes where you dispense that. I think that's what Tesla does. If you go near the Tesla supercharger in Scotts Valley, there's like this fenced off area with huge transformers, which of course there have to be huge transformers. They're hitting the big wires, and the chargers themselves are fucking tiny, dude. You know, like a charge cabinet's big, and so when you look at their chargers, you think there's no fucking possible way they could have the power electronics in here, and they don't. It's just a dispenser point, and I don't think there's any fucking lights on it or anything. You might want to think about that. Keep your power electronics in the dark. Keep them sealed, or vent them and pot them, or, you know, whatever. There's lots of ways to do it. So, yeah, electricity. I've worked all the equations for things like, you know, how am I so sure of since I'm not an electrician, how am I so sure of myself that the neutral current can never exceed the L1 or L2 current? Well, I'm a fucking electrical engineer, dude, of 22 years practicing with a Bachelor of Science in Electrical Engineering and a Master of Science in Electrical Engineering. You know how many of these circuits I've crunched? Do you know how many AC and fucking circuit analysis circuits I've crunched? thousands, dude. Like, are you kidding me? I can just look at it and see the answers. Like, you're not understanding how much math I've done around DC circuit analysis and how the current branches through the various branches with, LRC, so inductors, capacitors, and resistors. So the most basic is DC with resistors. And then you can go DC with capacitors and DC with inductors. And then you can start adding in transient analysis, like what happens at T0, what happens at T infinity, what happens at any given point in time, right? You can graph all this stuff. Then you get into AC, and you can get into all kinds of advanced first, second, third order analysis of these circuits. We were simulating back in the day, like, when was 9/11? 2001? Like 1999, 2000, 2001, simulating the fuck out of that shit. At the time we were using mostly MATLAB, but there was also, there was two big competitors for circuit simulation. Let's see if we can pull those up. This is after PSpice, and they're all based on Spice, but doesn't matter. I could look it up in some kind of fucking history page, but there was two main circuit simulators. They worked okay. The problem with most of those is they're basically ideal circuits, and so in order to get them to behave exactly like your real circuit, you have to enter so much fucking errata, dude. It's like you have to enter like 72 pieces of information in order to get accurate modeling, and then you have to have a tool though after the model, and it takes like fucking 45 minutes to compile, dude. It's just not worth it. What you do is you add margin and apply rules of thumb, dude. All electrical engineering, if it's not like RF or something like that, dude, it's all rules of thumb, dude. Like the thing I told you about power resistors, if you just understand one thing or two, the first thing to understand is the way heat works, the way heat is created, the way heat moves, the way heat is dissipated, the way heat affects a given thermal mass, what thermal mass is, what thermal transfer is, generation and management of heat. That's the keystone that all tradesmen know or don't know, but they all know it, right? They don't know that that's what they know, but by God, when they tell you make a fucking swaged crimp, that's thermal management, dude. It's less, we speak of it in terms of carrying current, but we don't really care, right? You could make a sloppy crimp. What's important is if you're producing heat right there, that you get that fucking heat out of the junction. And then of course that it doesn't corrode over time, blah, 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 blah. The second thing to understand, once you fully and completely understand heat and I squared R and inefficiency and all that shit, I was gonna, that one's so much more important that I'm not even gonna list the second, because I was gonna talk about like understanding, breakdowns and voltage, and how important like the cleanliness of something is, right? Like something can stand off 100 volts all day long if it's clean and conformal coated. Like if you scrub it with a 99% alcohol and you conformal coat it with an off-the-shelf silicone or acrylic conformal coating, you can get incredible standoff, dude, in the tiniest space. But if you leave things bald, covered in flux, dude. Anyways, yeah, forget the second one. Just focus on understanding the creation of heat, because what causes fire in a circuit? Heat. Fire needs heat, fuel, and oxygen. Oxygen and fuel are there all the time. The only reason a fire starts is because of heat. Heat comes only from current, dude. All right. Voltage can create heat. This is why you have to understand voltage. Like, think about like a lightning bolt, right? But that's kind of like a flash in the pan, right? Like, what's really generating the heat is when the voltage is doing work against the load and the current's flowing, and the current squared creates the power. So even though voltage, like, here's a perfect example. You know those globes where you put your finger on there and the lightning bolt comes to your finger? Very little heat, right? Like zappers, that's not work being done. Work being done is carrying a 5-gallon bucket up a ladder to the roof. That is work completed, right? So current flowing is the fucking definition of fucking work completed, dude. And I spent, decades of my life understanding AC, and just look around. All of your modern brushless power tools and brushless e-bikes, do you know what that is? That's nothing more than a DAC, dude, running on some MOSFETs. It's a fucking microcontroller with a digital to analog converter, which means just a microcontroller PWMing effectively, right? To the gate of a fucking H-bridge times 3. They're all 3-phase. Again, there's a few that are 6-phase, but dude, 99.9% of motors are just 3-phase motors. They're brushless stepper motors. Now they're wired, they're wound funny, and whether the outside spinning part is the magnets or the inside part, well, let me think about this. So you have an outrunner. That's the magnet ring spinning around the I want to say the coil, the stator. And then you have an inrunner, and that's what the magnet is spinning inside of the stator. So the stator has to stay still because there's no brushes, right? So the stator, you can have an inrunner or an outrunner. And it's nothing more than a little 3-phase motor. And the simplest way to drive it is trapezoidal drive, dude. You literally just go, just fucking turning that shit on and off. And then you can get more sophisticated. That's why I say it's nothing but a DAC. That's harder on your MOSFETs and requires some tuning. Huh? So, in terms of practically testing these, theories I have, some guys, it's funny, dude. Some guys who have a stick up their ass or a chip on their shoulder think that just because I'm an engineer, they'll be like, oh, well, his theories, It's like, bro, they're not fucking theories. There's no one more proven in the industry than myself. Look around. Bet you like those brushless power tools, don't you? Bet you like those brushless. Have you ridden an e-bike yet? Like a 40-mile-per-hour e-bike? You shut the fuck up till you ride one. You'll find out about efficiency, dude. And fucking cutting flux, dude. Yeah, I started smoking on camera, dude. It's one of those fucking quarters. I got too many irons in the fire. I'm fighting on many fronts, dude. You have no idea. Well, we survived another hour on the road. Where are we at? Time 53 minutes. Only reason I shared this information is because invariably I pick up like I said, I got like 420 subscribers, right? That means 4.2 of them are actually watching, and lots of times it's some young guy who wants to get into it, dude, and he knows I've gotten into it, and they're looking for fucking hints and tips and tricks, and I just want to remind you, like, shit's real. You will get electrocuted. You will start fires. There will be fucking sparkles. You will fucking have shit blow up in your face, Don't be thinking you're just gonna go fucking slamming boxes, right? Like when I'm like, dude, slap a 10-4 into a 4-inch jobby, fucking stab it on the box. Don't think that you're just gonna go do that, dude. You're gonna fuck up and slap the wires, dude. You're gonna fucking throw sparkles in your face. You better wear eye protection. Wrap around, shooter's eyes. They're like $2. Or fucking go anywhere and fucking steal them, dude. Any place that's legit has to have those fucking eyes around, and nobody wants to wear someone else's eyes. So you put them on, and then you put them in your top pocket, dude. You can even come to MySpace and steal a pair of glasses. If it means it will protect your eyes, please do so. Because no one wants to wear fucking someone else's cheese glasses, dude. Off your fucking nose cheese. They don't want your nose cheese on their nose. It's like $2, dude. And those fucking eyes last months, dude. I recommend you not work with gloves. It'll give you a false sense of security, and you'll finally poke through, or you'll use your gloves for something else and they'll get wet, or you'll fucking tear a part of your gloves and you'll get bit. Don't get used to handling 240 120 with fucking gloves, dude. That's stupid. I work barehanded. Wearing rubber shoes, you know, but I fucking haven't been bit by AC in as many jobs back as I can think of. Last time I got bit, well, that's the funny thing is I tend to forget. When was the last time I was bit by AC? Oh, yeah. I got bit a bunch. Working wet, dude. What the fuck was I doing? Working with pumps, wet, out in the fucking rain. All right, something to do. Plugging and unplugging fucking cords in the rain with pumps, pumping water with fucking no ground, you know, in those situations where I've got like an L1 neutral circuit and no earth, and I'm fucking, you know, soaked and the ground is soaked, dude. Just getting fucking lit a little bit. Just, it's nothing, dude. I had a socket get wet in the last year and dump a bunch of fucking voltage onto case such that it bites you a little bit. Those aren't large current producing. Those are tickles. If you're an emerging engineer or you're in the trades and you want to listen to what I say and find one little fucking mistake that I've made or some person who disagrees with me someplace, just get the fuck out of here. If you want to, you know, do whatever you're doing and hear me grumbling in the background and every once in a while tune in and be like, oh, wait, that's something I'm interested in, and kind of listen and then formulate a question and ask that question, then I'll answer it to the best of my ability. Like, you jump on my YouTube page or on my forum or on my web page or call me or text me or whatever, dude. If you have some question, it involves like safety or, you know, like sketchy stuff, I'll tell you exactly what I know. You're honor bound to share with someone else your fucking learnings about, like, you know, what works and what doesn't. No sense in having someone learn fucking hard lessons with stuff that can kill you or start fires. You gotta be real fucking diligent about it. Lawnmower man.